In this video, we're going to take a look at something called level curves, which give us a way to understand three-dimensional surfaces by looking at them in 2 dimensions. Topographical maps give us a way to understand three-dimensional space in 2 dimensions. On a topo map, every point along a line or curve on the map has the exact same elevation. Level curves give us a similar way to understand surfaces that are defined by 2 variable functions. If we take a look at a 3-dimensional surface, we can then place lines along that surface for varying values of z. Once those lines are in place, if we take a top-down view, in other words, if we examine that surface in only the xy plane, we can see those lines that we've placed on the surface in 2 dimensions. These lines are what we call level curves. They create a 2-dimensional view of our surface, where along every line, we know that every point on our graph has the same z value. So for a given function z equals f of xy, we're going to define the level curve at height c to be the set of all points xy belonging to R2, so that f of xy is equal to c. That definition leads to a pretty straightforward way to find the level curves for a given surface. To do so, we'll pick a few values of c. We might pick them to be equally spaced, but there's also times when you may choose them not to be. We're then going to solve a series of equations of the form f of xy equals c and see what curve that gives us in the xy plane. We can graph that, label the curves, and then we can interpret what those curves are telling us about our surface. Let's take a look at an example. We're going to consider the surface f of xy is equal to x squared plus y squared. We know that if we write that as z equals x squared plus y squared, that because we have a linear term in z and things are added together, that this is, again, like we saw in a previous video, this is an elliptic paraboloid. And in particular, it's a circular paraboloid because our traces would be circles if we go perpendicular to the xy plane. Let's look at, in particular, the level curves for c equals 1, 4, and 9. So what we're going to do is we're going to replace z with those values. So our first level curve is a circle centered at the origin with radius 1. When we replace the z value with 4, we get a circle centered at 0, 0, and this time we have a radius of 2. If we replace it with 9, of course we get the same thing, a circle, but now our radius is going to be 3. So if we took a top-down view of this elliptic paraboloid, with these lines sketched on it for z values of 1, 4, and 9, we would get a picture that looks like a circle of radius 1, a circle of radius 4, nope, 2, so that's too big, a circle of radius 2, and then, of course, a circle of radius 3. In this next example, we have a slightly different shape. Here we have x squared minus y squared. So if we think back to quadric surfaces, if we write z equals x squared minus y squared, this is going to once again be a paraboloid, but this is a hyperbolic paraboloid. And that description is going to be related to the level curves that we see. So here we're asked to examine the curves for c equals 1, c equals 0, and c equals negative 1. So when c equals 1, we have x squared minus y squared equals 1, which you should recall is a parabola, and it is a parabola that is shaped like this. So its major axis is going to be along the x-axis. That's not an awesome picture, but hopefully you get the idea. This is definitely not my strong suit. Whoops, that's even worse. There we go. Now, when we do c equals -1, we're going to get x squared minus y squared equals -1, which is, of course, the same thing as y squared minus x squared equals +1, which reverses our major axis for our hyperbola, and now we're going to get, that looks like this. So this sine of c is going to shift the axis along which our hyperbola is centered. When we plug in c equals 0, we get x squared minus y squared equals 0, which means that x squared equals y squared, which of course becomes x is plus or minus y. And so those are two straight lines. We're going to get the line through the axis with slope 1, and the line, or not through the axis, through the origin, with slope -1. So our level curves look like this for this particular hyperbolic paraboloid. All right, in this last example, we're going to take a look at a little bit of an application. So we're going to be examining we have a contour map. Clearly, this is not a real contour map, but use your imagination. And we're going to use it to answer the following question. So it says, which point is at the highest elevation and which point is at the lowest? So what we want to look at is the level curves. And we can see that points A and C are on a level curve that is marked with 12. So what we know, it says in the legend on our map that we are measuring elevation in hundreds of feet. So both A and C are at an elevation of 1,200 feet. While B is at an elevation of 1,000. D is at the same elevation. And E is at an elevation of 600. So clearly the highest are going to be points A and C. And then it says, does moving from A to B represent a larger or smaller elevation change than moving from B to E? So moving from A to B, we're going here. And of course, we don't necessarily have to consider this a straight line distance. And then moving from B to E, we're moving from here to here. So A to B is a further distance, but from A to B, our elevation change, we went from 1,200 down to 1,000, so that's a 200-foot elevation change. From B to E, we went from 1,000 to 600, which is a 400-foot elevation change. So even though the distance appears to be shorter, the elevation change from B to E is actually the larger one. So summarizing what we know, level curves give us a way to examine three-dimensional surfaces using two-dimensional plots. So we're going to pick some values of C, we'll take our function and set it equal to those values, and we'll examine what those curves look like in the XY plane in order to understand how the heights along our actual surface are changing. We'll see in the very near future that our level curves help us to see where our surfaces are increasing or decreasing the most rapidly.